Hello, everybody. So we are going to talk about the average value of a function in this video. So let's start with just a reminder that's going to help us kind of understand what we should do of what an average in general is. All right, if you have some quantity, some list of some type of quantity, like maybe heights of people, let's call those y sub I, and then is the height of the ith person. If you wanted to compute the average value of the height of this group of people, you would simply add up the height of the first person, height of the second person, until you get to the nth. I'm assuming there are n number of people, whatever that is, and divide by n, right? Which we can write as 1 over n times this sum, right? But of course, we can use nicer notation now. We've got summation notation. This is just 1 over n, I equals 1 to n, y sub I. All right, so that's the classic idea of an average, right? That's the one we're used to. However, suppose we had a little bit different of a situation. Let's suppose that I had a stretch of road, right? So maybe I'm looking at a side view of this road, right? And I want to know its average value, say, from this point on the road to this point on the road, the average height of this road, okay? That's a much trickier problem, right? So what can I do? I don't have a number of roads to add up their heights. I have an infinite number of places on this road in order to measure its height. So let's give this a little structure and come up with an idea. I'm going to put this little picture of my road over an axis. Let's make it black, a little thicker. And let's label some things. So let's say now I'm looking at this picture of the road, but I've put it over an axis. I can make this graph be a function. Let's call it f of x, which is the height of the road at position x. Okay. And along here, this is our x-axis at each position. Let's just give labels to this interval that we're talking about. Call it A and B, our traditional endpoints. So I want to know the average height of this road, which in this case is our function over this interval. So what could I do? Well, I can't measure it at every single spot. Right, at every single, there's an infinite number of spots along this road, right? But what I could do is set up an interval, right? Maybe I take a measurement every meter along the road, right? And the average at each point, right? So if not the average, the height at each point, right? So if this is x sub I, right, then its height is just the value of my function, f of x sub I. Okay, so at each point we have height f of x sub I. I could add up each of those heights and then multiply by, just like we did over here, the number of the reciprocal of the number of places where I measured, right? So if I got 100 measurements, I would add up all the heights and divide by 100, right? So we're just following very closely what we did up here. Okay, so far so good. Now let's play a little game with notation. Remember this interval here we usually call delta x. And we know delta x is b minus a divided by the number of intervals we have, which is another way of saying n is equal to b minus a over delta x, just playing with algebra here? Well, I can put that expression into this formula for the average function that I have. Let's actually take this one step farther. If n is b minus a over delta x, then 1 over n is equal to delta x over b minus a, right? Just taking the reciprocal. So this 1 over n becomes delta x over b minus a, n equals, I equals 1 to infinity. Pardon me. I equals 1 to n, f of x sub I. But of course, we can use our rules of summation and move the delta x inside, and we'll get f average is approximately 1 over b minus a, I equals 1 to n, f of x sub I, delta x. Okay, so we just did what we would think to do if we were trying to find the average of this road. We just measure it at a few spots and take the average and hope we haven't missed any large changes in height in those intervals. Of course, we get a better average if I measure at more spots, right? For instance, if I only measured at one spot, maybe the one spot I measure is right there, it's just way too high. And maybe I take an average where I measure at the end point, somewhere in the middle, and that it's still not a great understanding of what the actual height is. So the more intervals we take, as usual, we're going to get a better approximation. So what we'll call the average value of this function is taking the limit as n goes to infinity. And as we do that, we notice what this sum over here looks like. This is a constant, 1 over b minus a stays the same. The sum in the limit becomes an integral, and it tells us exactly how. We'll take this to be our definition of the average value of a function. So there's our average value. It's simply taking the integral over the average value over the interval. And we simply take the integral over that value, over that interval, and then divide by the length of the interval, right? So the length of the integral is like adding up all the values. The length of the integral is like dividing by how many there are, right? So it does actually, I think, make some nice intuitive sense when you think of it that way. All right, so let's do one abstract example that might convince us that this is the right thing to do. Suppose I had a function, let's say x of t is the position function, right? So it tells me where something is at time t. Then x prime of t, we know, is the velocity. Okay. Suppose we want to know the average velocity. Let's compute the average velocity from t1 to t2, right? Between two times. Well, I'm just going to use what we have here. V average is 1 over t2 minus t1, the integral t1 to t2 of v of t dt. However, we know an antiderivative of v of t. It's x of t, right? That was the whole point of, that was the whole place that v of t came from. It's the derivative of x of t. That means that this integral is x of t evaluated from t1 to t2. So what do we get? Our v average is equal to 1 over t2 minus t1 times x of t2 minus x of t1. Let's just write this one more way. X of t2 minus x of t1 over t2 minus t1. Okay. We should recognize this, right? So first of all, let's think about what the top is. It's where we were at the end of the interval minus where we were at the beginning of the interval. In other words, it's our change in position T2 minus T1 is what time was it at the end minus the time at the beginning? How much time has passed? The average velocity is just our change in position divided by the change in time. And that's just the definition of average velocity. And so this formula we came up with works perfectly in this case. You also might recognize this as the slope of the line between 2 points on our velocity curve. If this is our velocity curve, and we were trying to figure out the velocity between here, sorry, our position curve, and we were trying to figure out the average velocity, it's simply the slope of the line connecting these 2 points, okay? And that might also be a familiar concept. Okay, let's do one more problem with a little more structure to it. Okay, so let's just figure out, not more structure, that was the wrong word. Let's just do one concrete example, say with actual numbers. Let's just find the average velocity, or the average value of the function g of x equals x minus 1 squared on 0, 3. Okay, so the average velocity on this interval is the oops, I forgot my 1 over 3 minus 0, the b minus a, times the integral 0 to 3 x minus 1 squared dx. We can figure out this antiderivative. It's going to be 1/3 x minus 1 cubed. You can use a u sub on that. If you need to, you might see that this is certainly the antiderivative. The 3 comes down, cancels with the 1/3, leaving us squared behind. And we evaluate from 0 to 3. 1 over 3 minus 0, I should probably stop writing that minus 0. And then I've got 1/3 of, so 3 minus 1 cubed is 2 cubed, minus, let's just factor the 1/3 out of both of these, minus 0 minus 1, or negative 1 cubed. I'm missing, yes. All right, so 1/3 times 1/3 is 1/9. And then in the parentheses, I've got 8 minus negative 1, which is 9. So we end up with 9 over 9, or 1. Now, all right, so that's first thing. That is just a definition. G of x equals 9, right? G average equals 9. So over the interval 0 to 3, the function g of x equals x minus 1 squared has an average of 9. Let's look at one more thing having to do with this function. Oops, my mouse just started moving very, very slow for some reason. But in any event, that's all right. So let me share this picture with you. Okay, so here's a picture of this function. Sorry, everything has decided to stop working all of a sudden. I'm not quite sure why. Ah, there it is. Okay. Let me remove a couple of things. All right, here's our function. Okay, this is the function x minus 1 squared over 0 to 3. We found the average value to be x minus 1. Let's get really good. Sorry, y equals 1. Okay, so that blue line represents the average value of 1. The red line is our function. One way to think about this is if we found the area under the curve of f of x from 0 to 3, this pink area or red area, it's the same as the area underneath that line from 0 to 3. Those are exactly the same area. okay? And so that's a nice geometric interpretation of what the average value is telling us. It tells us what is the constant function that has the same the same amount of area under it, right? Which is a geometric way to think about what we talked about in the first example. The average velocity versus the actual velocity is, you know, when you drive a car, your speed is going up and down. And at the end of 2 hours, if you've gone 100 miles, it's the same as if you were in a car that was going exactly 50 miles per hour the whole time, right? A constant velocity function. So this is like the constant function that accomplishes the same amount over 0 to 3, while our function gets very little area in the beginning, almost none. It gets no area at 1. Then the amount of area it's getting per unit is increasing, and it's getting much more area at the end. On average, it's as if it got 1, right, an amount of 1 area per unit there, okay? All right, that's it for this one. Thanks, everybody.